Hello, everyone. Welcome to this presentation. I am Siyuan Xing from the Department of Mechanical Engineering, California Polytechnic State University. Today, I will be presenting the independent periodic motion arrays in a 2 degree of freedom nonlinear regenerative cutting model. In this presentation, I will first give an introduction about machine tool vibration, and I will construct the physical model to predict the periodic motions. The original differential equation will be discretized and used for form the implicit mapping structure to represent the periodic motions. Once the periodic motions are obtained, I would like to talk about the stability and the bifurcation conditions of such periodic motions. As a result, I will present arrays of periodic motions in the machine tool system. To validate the prediction, the numerical simulations will be carried out and provided. So finally, I will wrap up this presentation. So the study of the nonlinear machine tool vibrations starting from 1974, Hanna and Tobias, they observed the nonlinear behaviors of the machine tool system in phase and milling process, introduced a cutting model with nonlinearity from the structure and cutting force. In 1984, Xing and Tobias developed a machine tool vibration model with force nonlinearity from the separation of tool and workpiece. In 2007, Innsberger and Tao presented a 2 degree of freedom regenerative cutting model with state-dependent delay. The aforementioned studies only consider the self-excited vibration of a cutting tool itself. The oscillation of the workpiece is not considered. In 2006, Chen and Shao studied effects of workpiece deformation on machine tool vibration in turning process, and they report that the workpiece deflection can have significant effects on the turning stability, especially for a slender workpiece and high-speed machining. In 2007, Dasnayak and Su presented a regenerative nonlinear cutting model encompassed the workpiece whirling, and pure doubling bifurcations were observed. The cross-coupling between the tool and workpiece makes it difficult to apply traditional analytical methods for machine tool vibration. Recently, a semi-analytical method has been developed for periodic motions in nonlinear systems, and this research is based on this method. So in terms of the physical model, it is presented on the left-hand side. So we have the machine tool system represented, we have a machine tool represented by a 2 degree of freedom mass spring damper system, where the spring is the nonlinear spring. And on the right-hand side of the figure is the workpiece, and the dark gray area is the raw surface, and the light gray area is the cutting surface. And this black solid lines on the cutting surface represented the surface by previous cut, and the dashed line is for the surface by current cut. The difference between the previous cut and the current cut is the cutting thickness. So the B here is a difference of xt minus tau minus xt. During the cutting process, we assume that the workpiece is oscillating, in the horizontal direction, and the displacement of the workpiece is represented using Q naught cosine omega t. This can happen if you apply the periodic excitation to the workpiece, or you may think it as some external disturbance applied on the workpiece. So the cutting force F is determined by the cutting angle and the cutting thickness, and we assume that cutting angle phi is a constant during the cutting process, and the ds is the cutting thickness minus the static cutting thickness. So we can have the equations of motion in this form and writing it in the state space form. So we are considering the periodic motions in such a system. To compute the periodic motion, we're going to first discretize the original system using the middle point discretization scheme. From there, we can construct the implicit mapping pk at the time interval tk minus 1 to tk. So the corresponding algebra equation for the mapping pk, we use the gk to represent it. And it's a function about the current state, previous state, the xk minus 1 xk, and the corresponding time delay state. And the p here is for system parameter. And the explicit form for gk is represented in the equation below. So for the time delay nodes in the algebra equation gk, because those time delay nodes are on the periodic flow, so we can use the two nearby non-time delay nodes to interpolate these time delay nodes. In this study, we use a very simple Lagrange interpolation. So the periodic motion can be represented as using the composition of the implicit mappings from P1 to PMN. Using this mapping structure, we can map the initial point to the last point. So this set of the discrete nodes on the periodic motion can be computed using the sets of algebra equation, the gk and the interpolation function, and the periodicity condition where the initial point overlaps with the last point. So lowercase m here represent the pure M motion. So if M is 1, it's pure 1 motion, so on. And we can have also pure 2 motion when M is equal to 2, and pure 4 motion when M equals to 4, and so on and so forth. Once the periodic M motion is determined, and we can discuss the stability of periodic M motion. We'll first linearize the equation gk, and we need to define a new variable yk representing the time delay history at a time tk. So the resonant Jacobian of the periodic flow can be represented, can be determined by using this dp function, which represents the variant of the delay history at the last moment with respect to the delay history at the initial moment. So the dp function, the eigenvalues of dp function can tell us the stability of the periodic motion. When all eigenvalues are within unit circle, then the periodic motion is stable. If one of them is outside the unit circle, then it is unstable. And we also can determine the bifurcation conditions such as the Saddle bifurcation, periodic double bifurcation, and Lamach bifurcation from those conditions. So here I would like to represent some the result we obtained in the machine tool system, and the parameters are listed below. And in this two graphs, we present the horizontal displacement and versus excitation frequency. So the points plotted on those two figures are the periodic nodes, such as x0, xn, and x2n, and so on and so forth. So we see the horizontal displacement, the x, varies, the periodic nodes varies with the excitation frequency. In those two figures, the black solid line are for stable periodic motions, and the red dashed line are for unstable periodic motions. So we have the branch of pure 1 motions starting from 0 and then go all the way to infinity. And in this figure, we also observed the two area which contains the arrays of periodic motions. So on the right hand side, this is the room picture for the area Z1, where we have the cascaded periodic motions. So from from P2, P3, P4, P5, P6, and then all the way to the chaos, and then return to the pure one motion. So in this region, in this small region, we have the periodic motions from 6 maybe all the way to chaos. So here I only represented the pure from pure 2, pure 6 motions. Okay, the next slide shows the area of the periodic motions in the zoomed area in the second area Z2, and we have the so periodic motions from right to left, and starting from P1, P2, P3, P5, P4, 5, 6, and in this area, okay, small area, we will have the periodic motions from P7 and all the way to chaos. And they are not represented, they are not presented okay, in this figure. So next I wanted to show some simulation result and to validate our prediction. So what is presented here is period 2 motions when the frequency is at 43 hertz and Q naught is at 0.15 millimeter. So the first figure is showing the phase trajectory in the horizontal direction, and the second one is the phase trajectory in the vertical direction. And this is for a period 2 motion. So in those two figures, the black curve are for the numerical simulations, and the analytical solutions are presented using this white circular symbols, and these blue symbols are for the initial delay history, and this DIS means delay initial starting point, and the DIF is delay initial finishing point. So we see the periodic motions starting from here and rotated for 3 circles in the horizontal direction, and in vertical direction the motion looks a little bit more complicated, but the displacement in the vertical direction is much smaller than the displacement in the horizontal direction, which means the vibration in the horizontal direction is much stronger than that in the vertical direction. So next slide is showing the time history of the horizontal displacement and the vertical displacement. And we do see that the difference in the vibration amplitude and also their general shape of the time response. Next slide, the first figure on the left shows the displacement trajectory. So x-axis is horizontal displacement, and the y-axis is the vertical displacement of this period 2 motion. The second graph here showing the cutting thickness variation with time, and the cutting thickness for this period 2 motion is between around the 0.3 to positive 0.3 to negative 0.3 millimeter. So it's relatively large, and the vibration is relatively strong for this period 2 motion. So we also did used the Fourier finite Fourier series to represent the periodic motions. And the first figure in this slide is showing the harmonic amplitude versus harmonic orders, and these gray circular symbols are for horizontal, the harmonic amplitude in horizontal direction, and the red one for the harmonic amplitude in the vertical direction. And we see generally the amplitude in the vertical direction, especially for the higher order terms, they are at least 1 order of magnitude smaller than that in the horizontal direction. And this is on the right hand side. This is the comparison of their harmonic phases for the horizontal and the vertical directions. All right, so in this presentation, the periodic motions in the periodically forced 2-degree of freedom nonlinear machine tool system were obtained. The corresponding stability and bifurcations of periodic motions were discussed. To validate the analytical prediction, numerical simulations of periodic motions were carried out. That's all for for this presentation. Thank you for your attention, and I will be happy to answer your questions.